Hello and welcome to another exciting chemistry session. This is your host, Mr. Monson, chemistry tutor. So we're still in the series of atomic structure, and today I'd like us to just run through quickly what we call uh, isotope or isotopes. So our learning objective today is uh, just two. One to describe what an isotope is, and then want to look at the wide application of what we call radioactive isotopes. So to begin with, start by describing what an isotope is. So an isotope, we can say isotopes are atoms of the same element. So atoms of the same element that have the same proton number but different neutron numbers. So an isotope can be defined in two ways. We can define an isotope in terms of neutrons and protons. Again, we can define an isotope in terms of mass number and proton number. So what we're looking at in this particular slide is the definition of an isotope in terms of proton numbers and neutron numbers. So we're looking at chlorine 35 and chlorine 37. So according to the definition, we say isotopes are atoms to start with. They are atoms of the same element. So what do they mean by the same element? The same element, so this is chlorine, this is chlorine. So atoms of the same element. So in the element, which is a chlorine, it happens that you have an atom of chlorine with a 35 and an atom of chlorine with a 37. But what is important about these two atoms is that they share the same proton number. So if you look at the proton numbers, they both have 17, 17. Now, in terms of neutron numbers, we'll notice that for neutron numbers in a chlorine 35, it will be 35 minus 17 and we get 18. Then in a chlorine 37, it will be 37 minus 17, which is giving us a 20. So basically what is different are the neutron numbers, but the proton numbers are the same. So that is one way of defining an isotope. Then the other way is where we talk about the mass number. So in terms of mass numbers, we're going to notice that there is a chlorine 35, a chlorine 35 and a chlorine 37. Now, according to the nuclide notation, we said what is always found on top of the nuclide notation is the mass number. So when we look at this chlorine has a mass number of 35. So it's Cl with 35 on top and then 17 down there. This is small letter L. Then the other one is Cl 37 on top and a 17 down there. So we're going to notice that these atoms of the same element, they have different mass numbers. So the mass numbers are not the same. The mass numbers are not the same, but the proton numbers are the same. So we can also define an isotope in terms of mass number and proton numbers. So an isotope, these are atoms of the same element. They contain the same proton numbers but different neutron numbers. They contain the same proton numbers but different mass numbers. So basically that is how we describe an isotope. So in the next slide, we're just looking at the definition which I was explaining. So we can define an isotope in terms of them having the same proton number but different mass numbers. So in the previous example, we have chlorine, both chlorines having a proton number of 17, but their masses are different. The other one is 35, the other one is 37. We can have an isotope of bromine. Isotopes of bromine, we have bromine with a mass number 79, but a proton number of 35. Another one with a mass number of 81 and the proton number. So we notice that the proton numbers will be the same, the mass numbers will be different. If we calculate the neutron number in these two, again, we're going to notice that the neutron number will be different as well. Quickly, we can talk about the application of these radioactive isotopes. Radioactive isotopes, not isomers. Radioactive isotopes. So, just to give a brief background about these isotopes, radioactive isotopes, we have elements that have a very unstable nuclear. We have elements that have a very unstable nuclear, and these elements undergo what we call a radioactive decay. So when these unstable elements undergo radioactive decay, they release three possible particles. They emit or liberate three possible particles. And these particles are the gamma particles, we have the beta particles, and we have the alpha particles. So these particles are now widely applied in the different industries. So radioactive isotopes are often used for monitoring the flow of materials in the production line. So sometimes, like in that example, we're talking about the paper mill. So in the paper mill, that is in the paper industry, they use these radioactive particles to monitor the thickness of the paper. So if you want to be producing the same thickness of the paper, then you use these radioactive isotopes to monitor the thickness of the paper that you'll be producing. Then we have what we call the GMT, which is the Giga Molar tube. This is another device that make proper use of the radioactive particles. So in case you have a leakage underground, and it's very physically, it's very difficult for you to notice that there is a leakage underground. So we use what we call a GMT. So a GMT is passed over the suspected area where you feel you might have some leakages, and then using the radiations, those rays, they'll be able to go in the ground and give feedback on the device to tell you which area is. It's like an X-ray. It shows you if somebody has got a fracture, if there's a broken bone. They pass through the radiations in the bones, and then it will be able to give a picture, and somebody will be able to see where there is a fracture or a broken bone. So that is the same principle that the GMT use. So it sends a radiation on the ground, and then it gives feedback on the machine, and it will be able to tell you if there is a leakage on the ground. These radioactive isotopes are also widely applied in the medicine and health industry. For instance, the treatment of cancer, when cancer is in just its early stages, we can use these radioactive particles to detect. So for diagnostic purposes, we use radioactive isotopes to detect if there is cancer. So these radiations are sent in the body, and then they give an image. So they give an image, the image will show the affected area. So we use the radiations to pick those signals. Again, you can use the same radiations to deliver therapeutic agents. If you want to deliver medicine to that affected area, you can also use the same radiations to deliver therapy that is in the biological body system. They are also used in the treatment of food. So if you want to kill bacteria and parasites, you can just run radiations, and then those particular bacteria and parasites will be killed. So basically that is what we wanted to talk about today, the isotopes and then the importance of isotopes in the many industries. So that's it for today. Until we meet next time, this has been your host, Mr. Munza. Bye bye.